Welcome to today's webinar. The topic today is optimization in RFEM 6 using blocks. My name is Andreas Hörold. I'm responsible for marketing and PR in the company Dlubal Software. For instance, technical content for the website, the German and English webinars, customer projects, and so on. I will be the moderator today and I will answer your questions during the webinar. My colleague Florian Hiddemann will do the presentation. He's responsible for the development of RFEM, the optimization add-on, and so on. Okay, I say some words how you can ask questions. At first, I switch off my camera that you can see the full screen. If you want to ask the question, just press that button with the question mark, then enter your question in that field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and then email questions to info@dlubal.com. Okay, that's at the moment all from my side. I hand over to Florian. Florian, it's your turn.
Thank you very much, Andreas, for your introduction, and welcome to this webinar about some new topics about the add-on optimization and cost CO₂ emission estimation. As you can see here, I would like to present you two topics today. The first one is these are some improvements we did in the last month within the add-on with some new functionality and little features. And the second one is meant as an inspiration for you to give you an idea how to use the optimization add-on together with our blocks. And yeah, I hope you enjoy it. And for all of you which didn't have so much contact with the add-on optimization in the past, I try to explain the basic features and the basic functionality during the presentation of the new features. So let's dive in with some slides at first, and after that we jump into the model to show it in the real example. So one new feature is, maybe you already know it, we have some results list where we collect all the single results given by a specific mutation of the model. The add-on optimization varies the parameters you would like to optimize and then save the result together in one list. And this list has now green check marks and red exclamation marks, depending if a model mutation is considered as valid or invalid. A valid model mutation is if you are using a design add-on in the background. This means that all verifications within the activated design add-ons, it could be that you use several ones like steel and concrete and timber together. And if everything is fine and the verifications you set it up in these add-ons are satisfied or fulfilled, you will see a green check mark. If there is a verification that is not succeeded below the 100% usage, you will see a red exclamation mark. And with this, you can really see have an overview which models fulfill your needs and which one not. It doesn't depend on the target value you set it up. There are some models that will have a lower target value where the verifications are failed, and the models where the verifications are valid, these are prioritized higher on the list. So if the target value is with 20.7 millimeters, for example, here in this mutation, this is bigger than the best one of a not valid model, and for the reason this is considered as green checkmark, it is higher in the list than the variant where the checks are not valid. So there is another type of calculation where you can see a red exclamation mark. And this is the case when we have a fail calculation, when something, for example, by varying some parameters, is not ready for a calculation and we have no results, independent if you have a design add-on active or not. So the second one, also regarding the result list, we are now collecting every result from all model mutations, even across multiple optimization runs. In the past, we started a new list every time when you started a new optimization run. And now we changed that. We collect now from every optimization run, every single calculated model mutation and store them in one list. It's now consistent, or you can say persistent, unless you change the model when the results are not comparable anymore. If this is not the case, we store them into one list, and I will show it later. It sounds a little abstract now, but in practical use, it's very handy if you need to abort or change some settings later on. For example, you can now also change even the optimization target. Yeah, so this is a very nice feature, and I will demonstrate it shortly. Another big thing is are the new sensitivity factors. A sensitivity factor is a number from 0 to 1 which represents the influence of parameters for the desired optimization target. So once you have some calculations and has done some pre-calculations of the model, the program is trying out different parameters and analyzes how these variations impact the desired optimization target. And a number which is closer to 1 represents that this parameter has a higher influence for the optimization target than a parameter which is more to 0. We use these sensitivity factors to allow you perform a multi-stage calculation mode. This one is also new. The idea behind is that you can calculate by varying the most influential parameters, and the program automatically analyzes for you which parameters are good to be varied. So it sets then in the first stage, it calculates an estimation for the sensitivity factors. And then in a second step, the program automatically activates some parameters, not all, depending what you have set it up in the configuration. I will show it on a small example now. So let's dive into the program. And as you can see here, the first model is a variable timber beam. This one has nothing to do with blocks at the moment. It's just for demonstration purpose of the new features I just explained in the PowerPoint. So what do we see here? We have a easy static system. Yeah, it's a single span member, and in the ends there are some members reaching out on the left and on the right side. It's a rectangular cross-section. And of course, when we are dealing with optimization, there are some global parameters in use. So we start here with a 280 by 280 cross-section with C24 wood, or timber material. And as you can see here, the cross-section width is given with a global parameter and the cross-section height also. In addition to that, the distance of the right support is also variable. Yeah, I can show you now here the overview for the global parameters. The beam length is just a constant, which is easier for me to make the model. And the left support distance here is just a constant. And we would like, in this little example, find optimal solutions for the right-hand support distance, which is now 1.5 meter, and for the cross-section width and height. This parameter here, the support distance, can be varied with 0.1 meter from the right side up to 2.9 meter, which is nearly in the middle of the beam. The cross-section width and height is going from 100 millimeter to 300, and it's going in steps of 20 millimeters. So you have 10 steps in between, and this is a variation this cross-section can take into account. So let's have the look on the first feature, recognizing valid mutations in the result list. So for this reason, I activated also the Timber Design add-on. As you can hear, Timber Design is activated, and yeah, I just made, for the demonstration purpose, easy loads. You see load case 1 with some self-weight, and there's another load case with a live load. We use here the German National Annex, of course, and a combination with that. So you can see design actions. It's all standard, which you are maybe used already, that we do some combinations and design situations for you. So you don't have to worry about all the timber design specialties. So let's calculate the system in the first place to see what we are talking about here. So now it's a standard calculation without optimization. You can see in each run later on, all these calculations are performed for each mutation. And as we can see in the governing results of the design add-on, everything in this configuration looks fine. Yeah. So, but we are here to find out if there is even a better configuration or not, and to use and play around with our optimization feature to see what is happening there. So let's delete these results and jump into the optimization settings. You can find it here under Calculate if the optimization add-on is activated. So you can store different optimization settings. Yeah, it's not necessarily one you have to fiddle around it. You can copy it, modify it, and use them for different purpose. This is quite handy because there are a lot of settings you can do, and yeah, so you can remember each different optimization run later on. So what do we do now in the first place? This feature I show you later on. This is the multi-stage mode, the multi-stage calculation. And even with this very simple system here, all mutations would have a total number of 1,815 optimization mutations. This is a lot if you consider that this is a very easy and simple system here. And for this reason, we are trying to develop more and more time-efficient strategies to find in a potential fast way the optimal parameters for you. Sorry. So just to show how this is working, we start with random mutations. And for example, I say just vary these parameters in a total random way and make it in total with 5 mutations. So as always, you have to set it up as active here with this checkbox and then you can start the calculation. So as you can see in the background, the first iterations are calculated. Each one of these mutations is also calculated within the Timber design add-on. And for this reason, you see model number 1, calculated with these parameters, didn't fulfill the design checks. Model number 2, like in our first example, fulfilled it. So with this algorithm here, it's just a random mutation. Yeah, here is no clear strategy for finding the optimal target value. The program at the moment is just giving random examples for these 3 values or parameters and collects all the results. So with this nice feature here, I show it, we can see easily which calculation fulfilled design checks and which not. And now if I cancel these calculation run here, today I will be mean to this model here and cancel it in any way. So what you can see here, the calculations you performed up to this point are stored. We have now 8 results. And as you can see here, the green check mark means it's very important to see it again. This model is now active, and because of the reason I canceled the calculation run, the add-on doesn't calculate the last cycle. So if you jump into a new model in the list, you have to calculate the model itself. We store only the results you can see here in the list. Obviously, we store not every full result which is calculated for each model. If you have a bigger model, that would be hundreds or thousands of results. But we collect the target value and everything you need to display this result table here. From this point, you can regenerate then your model because the add-on is varying the parameters like they are stored here in the way the model mutation shows it. So for this model number 7, I calculated it now, and here's a green check mark. And as you can see, this means that every design verification here, design check, is fulfilled. So let's see model number 1, for example. I change it here, perform a calculation to see what was going on, why there is a red exclamation mark. And as you can see, close, but it counts. The section proof here at this point on the left side is not fulfilled. So this is the way this list is working with these indicators here. The next feature, the results list, remains consistent. It's easy to show now because I canceled the first calculation run, and maybe at a later point, for example now, we would like to go for a new optimization run. So all I do now is say, okay, try to optimize it with a particle swarm, calculate 2% of the possible optimizations. As every time I make the optimization cycle here active. This is kind of a safety feature that you are really aware to perform an optimization run and not doing it accidentally if you calculate all. Okay, so what will happen next? Let's see. You can see the model, the results list here is stored. Yeah, there is no new list, and this is a small little feature, but very useful if you spend already some time with your model and calculate it, because now the optimization add-on checks each new mutation. And before it calculates it, it looks up into the result table and sees if this mutation was already calculated upfront. If this is the case, we jump automatically to the next mutation without calculating it. And if the model mutation is a new one, which is not stored in the list, the add-on just calculates it and edit it, like you can see here in the background. So as you can see here, now it's more straightforward because the particle swarm is a solving algorithm which tries to vary these parameters with the target value in mind. And yeah, the more you calculate, the more it is getting, let's say, a feeling, a mathematical feeling, which parameter needs to be adjusted in what way to achieve the best target value, which is at the moment the minimum member deflection at every point. So the 2.7 millimeters, let's have a look into the program and cancel it again. Where you can find it, because we abort the calculation, I need to perform a manual calculation of the system here. So let's see. Every design check is fulfilled. And for the target value, should be there. I go to the another model. Okay, yeah, I found it. Okay, we are looking for 6.6, and yeah, this is considered overall design situations. You set it up. So if I go to the maximum load here in design situation 1, the ultimate limit state, here you can find it's this part here in the members is 6.6, and this is considered as a target value. Yeah, it is looking for a global minimum to minimize the maximum member deflection at any given point. Yeah, I give you some time to let it suck in. And now we are able to find out the 2.7 millimeters. Just to be sure what is going here in the background. Yeah, you can see the 2.7 in this point. So this as a small introduction example for working with the list here and the ability that it stores from every optimization run. Let's go to the next topic, the sensitivity factors. What is going on with that? In the model now, we have 20 model mutations calculated. And now here in the table of the parameters to optimize, you can see some sensitivity factors. They are now estimated given by the model results list here. So we can now perform an analysis how the target value is influenced by varying different parameters. This estimation here is getting more accurate the more models you are calculating. And this small amount of 20 models, you can see the cross-section height should have big impact on the desired member deformation. And it's a much bigger impact than, for example, the cross-section width. And yeah, if you're familiar with how the stiffness in such a system is working, that's absolutely plausible, because the height of a cross-section is going with the third with the third order, and the width is going with the first order into account of the stiffness of this beam. So yeah, it's very a plausible result. And these two parameters here have much more influence than the support distance. Yeah, that's something you can already see in this little model. Here, it's easy to have an overview by yourself, but think of more complex situations where you vary different parameters, and you don't have a feeling what would happen if you vary different combinations. This is very nice to reduce the number of optimization mutations, because you can choose, for example, okay, if these ones are so impactful, why should I vary and spend my calculation time with this one? And as you can see, it reduces the number of optimization mutations drastically, because now it's 11 by 11 and not by 15 anymore. So here we have 121 mutations. And yeah, this is for the algorithm much easier to perform. More potential better mutations. So now the model, because I set it here in this dialog, only these two parameters as active, the model is fixing here the 1.5 meter support distance and just varying the second and third one. Okay, this as a basic introduction and remembering our new features. At this stage. So I can show you the multi-stage calculation as well, and for this reason I would go back into the settings, and we choose another optimization settings here, and now we have a look into these options here. The pre-calculation of sensitivity factors. For this reason, I will empty this list by varying the model. This is something you need to do now, because the list is stored. What I do now is I delete a load here. And if you change the model in a drastic way like this, all the results are deleted. So ensure that is something that will have an impact on your optimization results. So now we can start with a clean structure here. And for the next run, I say, please make a pre-calculation of the sensitivity factors. And in this example, we make only a small guess with, let's say, 5 mutations. And after that, the program should automatically combine 2 parameters in each following optimization run with the highest sensitivity factors. So it's kind of a bit abstract and complicated, like most of the things with this add-on, but let's see what is sticking behind. So now we have a multi-stage calculation. In the first place, we are doing the analysis. So the model is now varying some parameters with a very small amount of models to guess the sensitivity factors. Yeah, it's analyzing the results here and the impact, the estimated impact of these parameters to those result value. And as said before, the more mutations you calculate, the more accurate is this estimation. And now it goes to a second step. Yeah, it uses now the results from the analysis. And here it is now combining the two most influenced parameters with a particle swarm that calculates 10% of these possible combinations. And the 10% is now only 16, and it's not 181. Yeah, I'll show you it afterwards. And you can see after this optimization run, there is another optimization run waiting. And in the next optimization run, the program goes further and says, okay, I have now combined the most influential with the second influential parameter. And just to check it in another run, I go through and perform a calculation with the second best parameter and with the third best, because you choose to combine two parameters at the same time. And this is the strategy the program is choosing to go through these combinations. So the total amount of calculations is the first one from the sensitivity factors, 4 in this example. And after that, it's here 16, and then depending on the other value, around 15 to 20. And it's much less than 10% of all 1,800 model mutations. Here is only one. Interesting. So let's have a look into the dialog, what could happen here. As you can see, we have with only 17 calculations, quite some optimized results. But with a small amount of calculations, the sensitivity factors are not guessed very properly. Here it's now a very big difference on these ones. And you can do it better by giving here more accuracy of the pre-calculation with, for example, 30 mutations. So our recommendation here is to choose higher numbers if you feel the calculation is not so straightforward, going to the point afterwards. But this for now to demonstrate the possibility of our multi-stage calculation run. If you have already done more calculations, I switch to the same model here. And I did a pre-calculation. So we have here 217 calculated models. As you can see, the sensitivity factors here are more accurate now because there is a big result list which is analyzed. And this is more or less, much more plausible from an engineering point of view. What is interesting now is that that's also a nice feature. It's new because we have a consistent result list now. You can change the target value afterwards. So for now, we did the member deformation, the minimum member deformation at a specific point as a target value. So obviously, the height of the cross-section, the width of the cross-section, and the support distance. I'm sorry that these are here German words. If I would have translated them, the results would be deleted because it's changing the model. So I'm sorry for that, but I hope you can go with me. This is the support distance on the right side, the width of the cross-section, and the height. And obviously, the support distance should have no impact on the weight of the model, but the height and the width should be more or less equal, right? Let's check it. And we switch now to the minimum total weight. And as guessed, these sensitivity factors here are now changing, because now if you are varying the width and height, these influence the area of the cross section in the same way. And guessed correctly, it's quite equal. And the load distance or the supporting distance here from the right side has in reality absolutely no impact on the weight of the construction, because it's just a load bearing point. What's interesting, the more you calculate, the more this value will go to zero, because it's an estimation based on the list here, and our algorithm is already seeing with those amount of results that the influence of the desired target value is very small. So this is quite nice to see what you need to verify in your model to achieving specific targets. You can see here that in the list, if I change the optimization value and start a new run, so let's do it with a particle swarm. Just started. Let's see what happened. It's now changing. And this is also a strong feature. You can use all your existing calculations for this. So we have now 200 already existing calculations. And because we stored the target value in each previous optimization run, as well as the desired minimum deflection, if there are surfaces, the minimum surface deflection, and so on. So every available target value is stored with each mutation, even if you didn't activate it in the dialog. And this is very useful if you have different perspectives on your construction and you want to try out, okay, which one is the best for the minimum total weight and which one is the best for the minimum deflection. It's the first step into going to multi-target optimization runs. Behind the scenes, we are already thinking about those features, but it's a small step, step-by-step way going to these goals. Okay, so now you saw everything. We can change the optimization targets. We store it across different optimization runs. We have a multi-stage calculation mode, and maybe you are already waiting for the title-giving feature of this webinar, the optimizing blocks. This is just an inspiration because maybe you found out in the past, if you are working with global parameters, there are some restrictions, because global parameters are very, very useful to play around with the geometric of your model. And you can use it in so many input fields that are quite helpful to steer your model and create the geometric system you would like to have, and also can add static values, resistance values in many different ways. But maybe you experienced also some restrictions when it comes to demanding on construction rules. If you have a more complex statical system or construction you want to try out, you can use a block, because blocks are perfectly fitted to generate your model with your own specified rules, algorithm, programmable, and With a block, you can build your own configurator. And this configurator for itself takes input values. And the idea I would like to show today to you is using the global parameters as input values for blocks. And with this combination, you can achieve an optimization of structures which has some demanding construction rules within. So in the example today, we will not only optimize some small construction elements like you've seen before with the member, or maybe in the last webinar with more complicated members playing around with the geometry. We will try it out to give an idea what is possible with a more or less a simplified real-life steel hall. And in the steel hall, it will be possible that we play around with the number of the fields in length direction, and we'll play around with the number of the fields here in the roof area. The whole system you can see here is just one block. So thanks to my lovely colleague who created this, it's a real nice example what is possible there if you have the ability to play around in JavaScript at the moment. So at this point, I would like to make some advisement for next week. If you didn't have any contact in the past with blocks, in 1 week, there is a webinar from Andreas where he presents some features, including also the blocks in a more detailed and specific way. So if you're interested and to see more of blocks alone, maybe you can join the webinar next week if you have time. And for today, I will show you how to use the optimization together with a specified block. So I've done some pre-work here because this needs some time to set it up. And so I would like to present what I did here and to show you what is special about this model. So in this model here, as you can see, this is everything. It's a block. In the webinar next week, you can see, if not already known, how to edit it, how to import it from the Dlubal Center. Here for the moment, let's just stick with the idea. A block is a programmable object where you can define in JavaScript what is generated, what is steered. It's using internal features of our programmable API. And here at the moment, what you can see here is used JavaScript as a language for this. So as you can see here, the whole steel hall is defined with these functions and API calls. What is provided then, based on the structure here, you also define a parameter structure, and depending on what you are programming for the block, you have now your own input fields you use in your program. And this enables you to work with more complex structures. For example, this block is programmed in a way that automatically a bracing is activated. Yeah, you can see it here. If I unclick a checkbox, the bracing is updated. Yeah, it generates in the background a total new model. The numbering is different. Everything is different. So have in mind that you can play around this, just the borders within your fantasies and your and our abilities to work with JavaScript, obviously. But you can really do some fancy stuff with it. I set it up here, the input fields, to connect it with the materials, cross-sections, and everything which is in my model. And just here for the, let's say, a pre-calculation as an example, I added some easy and, yeah, it's leaning into a realistic load case scenario, but we are not rebuilding here our wind load generator or snow load generator. This is just for a demonstration purpose and to give you an idea what is possible with blocks. And yeah, if you have an engineering problem which is worth to spend some time with, which you are doing with a lot of repetitions, or you need to optimize it and there is something you would like to dive more into it, have in mind that you can program a block and then connect it with a global parameter. That's a trick for today here. I can just edit, for example, the number of spans in the width. So let's change this to 6, and we will see that here in the gable walls, the members and the bracing have changed completely. The whole structure of the steel hull is now different. I go back and change it to 4. So what I've done here is you can just use a global parameter in this input field. And as global parameters here, I have defined the span counts in the length direction and the span counts in the roof. Yes, and those values are defined as an optimization type. So this is a trick for today. We will optimize and play around with the span count, length, and roof, and vary them from 3 to 8 and 5 to 12. It's 5 by 7 steel hulls you create then in the background, and I will show you what is happening then if you use it in this way. So let's just go back here. Now, as explained, you can see in the construction what is happening. If I change this to 3 and this one maybe to 4, it's reconstructed. And this is, I think, a magic way to define even systems with different statical conditions, everything what can use a number, a Boolean variable, whatever you can use later on in a block and make complex, design complicated algorithm-based construction rules. And together with the power of the optimization tool, you play around with this block to achieve a global state of optimal target value. So let's go back and start with maybe 5 and 8. So I press apply and you see it's a totally new construction. So, but it, oops, I disconnected my table here. So this looks interesting, maybe, and I don't want only to consider different field spans, because if I choose less fields, I need stronger cross sections. And otherwise, if I have more fields, I would expect that my cross sections for the columns and the this bearings here on the coupling members has to be much smaller. So don't forget, you can use our optimization add-on in combination with cross sections. So let's say I want to use these cross sections in my block, and again, everything is generated and defined by one block you can see here. Yeah, I connected these cross sections here to the code in the JavaScript. And now I can go to RFEM and say, please optimize this cross section I used. Yeah, you only have to click here, and this enables the optimization feature for this member. Let's jump in the optimization settings. Here you can see, let's try it out. If you combine only the states for the length and roof, you have 48 steel holes, because it's taking also the minimum value and the maximum and the steps in between into account as a state. And if you multiply it with all possible variations of the cross sections, you get almost 500,000 possible steel holes. And who of you wouldn't like to calculate them all by hand? For me, at least, it would be painful. So I rely on the multi-stage optimization run and want to see if there is some construction winning the game for a minimum total weight. I want to have calculated in the later run only sensitivity factors which are greater than 0.5. And in the first run pre-calculated with 48 mutations. So let's just test it. Now, I'm totally aware that this is not the end of the story. If you have a system which is quite optimal in this way, and you have done many steel holes or comparable projects in the past, of course, you have to work in a more detailed and specific way later on. But it gives an idea what is possible if you program complex structures, because you can define almost everything which a design add-on is also needing in the background to evaluate this whole. And remembering our little green and red indicators here in the resulting list, the green arrow means that the first steel hole here is it's obviously heavy, but it's a first random mutation. This one is fulfilling all activated design verifications from the steel design add-on. So imagine you have a very complex structure with different blocks. You can put a steel hole as a block into it. You can put a small next building as a block next into it. You can adapt here some staircases as blocks. There are a lot of possibilities and steer them all by global parameters and then vary some calculations to get an idea, let's say in the first stage of your engineering progress, to try out different designs and find out what is going for a most efficient design. So this is happening here, and after the analysis would be done, the algorithm would then choose every sensitivity factor over 0.5 and combine it later on. It will done after this optimization run some other stages, but for the moment here, please have in mind the new feature is multi-stage. It's faster than only a single one with 500,000 of possible combinations, because it is more target orientated, considering the most influential parameters and only combining them in different multi-staged calculations. So in the end here, let's have a final look into the results I calculated with the steel hole in 3 to 4 hours here on my laptop. to see what is possible. In preparation of this webinar, I calculated this model here as well. We have 840 calculations. I think it costs around 3 or 4 hours here with the laptop. And as you can see, it's a very big variation of valid and non-valid models. And the baddest valid model is it's 100 tons with obviously a lot of fields and HEB 1000, some big profiles. It's a little, it's safe to be in it. And maybe a bit heavy, but also you can go down to 16 or 17 tons for a 20 by 16 meter steel hull. And yes, I have to say, in this optimization run here, I have only considered some ultimate limit states here. I deactivated for the time purpose the other design situations, but if you use it and let it calculate overnight, you can activate everything you need for a real life calculation you are using with RFEM every day. So it's just more time consuming than to let it run. But if you don't want to spend time on your local machine, let's remember you have also the possibility to calculate in the cloud. Next week, there's a nice webinar. Remember, cloud calculation and blocks. So you can also go to the cloud, and you have then these machines here available, and you can put your system into the cloud calculation, let it calculate, get the results after that, and it's then maybe a better inspiration how to adapt improvements on your model with this technology. And let's have a final overview from steel design. Here I also, in the block, there are no effective stability designs defined. You can, of course, do it. We just, in the preparation of this webinar, we just didn't do the whole job to add imperfections or the stability cases into the members, but you have here a full check of every other thing according to Eurocode 3. And as you can see, the best haul here with nearly 16.9 tons fulfills the design checks here, is given of a maximum usage by 99%. So this should it be within the time of 1 hour. I would like to thank you very much for attending this webinar today with me, and then I would like to give back to Andreas for the final outro. And thank you very much for attending. If you have any questions, then just write us and have fun to try it out by yourself. Goodbye.
Okay, Florian, thank you for your presentation. I've an additional hint for you. You can book our online courses to RFEM, Eurocode 2 or Eurocode 3. For more information, just press the buttons with the links at the bottom, or you can scan the QR codes. You can download this presentation as PDF from our website. You will get a link in the next days with the link to the recording, the slides, and the models. Okay, that's also all from my side. I thank you for your attention. Thanks to Florian again for the presentation. I wish all a nice rest of the day. Bye-bye.